Okay, to finish up this segment on lexicalized PCFGs, I want to talk about how we evaluate different parsing models and give some insight into how accurate these lexicalized PCFGs can be for parsing. So I'll actually describe two ways of evaluating a parser. Here's the first, or here's the basis of the first, and it's a very widely used method. So the key insight is that if we take some parse tree, for example the tree here, we can represent this as a set of constituents where each constituent consists of a label, a start point, and an end point. So if I look at this NP, for example, if I number the words in the sentence 1, 2, 3, 4, 5, this NP spans words 1 through 2 inclusive, and so this constituent is NP1, 2. Similarly, I have an NP4, 5, I have a VP spanning words 3 to 5, and I have an S spanning words 1 through 5. So this particular parse tree has 4 different constituents. Note that we do not include parts of speech within this definition. So we just look at levels higher in the tree than the parts of speech. So the short story is we can take any parse tree and map this to a set of constituents. We can do this both for human annotated parse trees, which will act as our gold standard in test data, and we can also do it for the output from the parser that we've built and which we're trying to evaluate. So let's now see how we can use this idea to evaluate a parser. And this is through basically calculating precision and recall on these constituents that I've just defined. So let's illustrate this with a specific example. So in general, I'll be in the situation where I have some gold standard tree for some test data sentence. Okay, so I have some test sentence and I have the human annotated tree. This is taken as being correct. And then I have some parser output, which is also a tree, which may be exactly the same as the gold standard tree, or may be partially correct in that it may include some substructures which are also seen in the gold standard tree. So both of these trees can be mapped to the representation I just described, so they can be represented as a set of constituents, where again a constituent consists of a label, a start point, and an end point. Now we can define various numbers. So I'll define G to be the number of constituents seen in the gold standard tree. In this case it's 1, 2, 3, 4, 5, 6, 7. And I'll define P to be the number of constituents in the output from the parser. In this case it's 1, 2, 3, 4, 5, 6. And finally I'll define C to be the number of constituents that are actually correct. In this case this is also 6. What do I mean by correct? That means that if I look at this constituent S18, for example, I can see that that's also in the gold tree, so that's a correct constituent. And similarly, if I go through each of these in turn, I'll find they're actually a correct constituent. It's worth noting that this method is general enough that it can allow cases where the number of constituents in the two trees are different. And that can be important because in reality that often happens. Just as an aside, if all of our rules were binary branching, so if we really had restriction to binary branching rules, the number of constituents in both of these trees would actually be identical. But in reality, in these tree banks, we allow rules which are non-binary branching, and because of this we may end up with different numbers of constituents in the two parse trees. Okay, so we've calculated these three numbers, G, P, and C. So now the recall is defined as 100% times C over G. So this is basically saying, of the gold standard constituents, how many of them do I recover correctly? In this case it's 100% times 6 over 7. The precision is 100% times C over P. In this case, 100% times 6 over 6. So this is saying, of the constituents you recover, what percentage of them are correct? So in this particular example, 100% of the constituents I recover are actually correct, but I've only recovered 6 out of 7. I think that's around 86% of these gold standard constituents. So this will be, you should do the calculations. I'm just doing this off the top of my head, but this is equal to 100%. Okay, so we've have some errors in terms of recall. We have 100% in terms of precision. So let me give you some indication of how well different parsers work under this particular metric. And this is using a data set that we've talked about a lot, the Penn Wall Street Journal Tree Bank, using about 40,000 sentences. That's, I think, on the order of 1 million words or something around that as training data. And then we have 2,500 sentences, which are test data examples. And again, to emphasize, each of these is going to consist of some sentence, some sequence of words, with a human annotated tree. And we're going to run our parser on these 2,500 sentences and compare the parser's output to these trees using recall and precision. We'll see of the constituents we propose under the parser, what proportion are correct, that's precision, and also what proportion of the gold standard constituents we recover correctly, that's the recall. Okay, so first result for PCFG is the following, and you can really see how poorly a PCFG performs. As I said, they were really a disappointment when they were first applied, low 70s in terms of recall and precision, and these parse trees look really quite dreadful, actually, if you look at the output from PCFG. This paper in 1994 was, I think, the first really accurate tree bank parser. It was due to David Madigan. It was created in collaboration with a group at IBM Research who produced a huge amount of seminal work in the early 90s on statistical natural language processing. One of the things they looked at was statistical parsing. So this is about 84% recall and precision. That was really a breakthrough result, way higher than these low 70s numbers. This is a very, very different model from the models I've described so far. It's a model based on decision trees and a sort of bottom-up parser. So we're not going into the details of this, but the main important point is that this was really the first serious tree bank parser, and it really worked quite well. The lexicalized PCFGs, I've described these results from my own work. My PhD thesis was on developing lexicalized PCFGs. They give results that are, again, significantly higher, so we're getting up to about 88% recall and precision. So this is really the number you can think of in terms of the accuracy of these lexicalized PCFGs. There are more recent results which have pushed performance further up into maybe the 91-92% range. I've listed a few different cases here. These two methods make use of discriminative estimation methods. And we'll see some of these methods later in the course when we see log linear models and conditional random fields and so on. And Petrov's method makes use of what are called latent variable PCFGs. But in both cases, there are close connections to lexicalized PCFGs, or certainly to PCFGs in this latter case.